All right, so the next presentation will be from University of Cambridge. It's reducing spatial error in mobile laser scanning by real-time uncertainty visualization and human-machine interaction. So we will watch the recorded presentation, and then one of the authors is here to answer the questions in person right after the presentation.
Hi, my name is Maciej Trzeciak. I am a PhD student at the Department of Engineering at the University of Cambridge, and along with Professor Chris Burgoyne and Professor Ioannis Bilakis, I would like to present a paper entitled Reducing Spatial Error in Mobile Laser Scanning by Real-Time Uncertainty Visualization and Human-Machine Interaction. To motivate my work, let's say that the digitization of geometry of buildings is a key element for many use cases in the architectural, engineering, construction, and operation industry. However, data acquisition using static scanners or photogrammetry methods is lengthy and requires even lengthier subsequent processing. A quick and apparent escape from this problem might be mobile, especially handheld mapping solutions, which are mainly based on LiDARs. However, the current state of practice mapping devices do not allow for scanning with high accuracy. Therefore, it is not uncommon that there is a mix of static and mobile scanners on construction sites, depending on the requirements of the use cases at hand. Alright, my method described in this paper aims at improving accuracy for handheld scanners. Now, let's recall that handheld scanners utilize something called SLAM, which stands for Simultaneous Localization and Mapping. SLAM is a class of algorithms that reconstruct the surrounding environment and at the same time localize the scanner within this environment. Interestingly, when a LiDAR is used, we can model just the trajectory of the scanner without explicitly modeling the surrounding point cloud. Now, such a trajectory can be modeled as a probabilistic graphical model. Here you can see one of such graphical models, and the whole problem is called pose graph SLAM then. Nodes of this graph, here marked with x1, x2, and x3, and so on, are locations of the scanner, and the edges of this graph are rigid body motions, marked here with z1, z2, and z3. Obviously, these rigid body motions are between the locations of the scanner. And for each location, we can store the corresponding LiDAR point cloud, here marked with PC1, PC2, and so on. And these LiDAR scans can make up the whole point cloud of a building if we compute the locations of the scanner correctly. And what's interesting is that we can also compute marginal covariances of these locations, here marked with sigmas. And those sigmas represent the uncertainty in the locations of the scanner. And here my method comes into play. The point of this paper is to provide a real-time method for uncertainty visualization in pose graph SLAM, so that the user can be aware of regions of potentially higher spatial error, and they can take corrective actions on the fly, so during scanning, and not when the scanning ends. To do that, this purpose region is a 95% confidence Gaussian eclipse, which is mathematically expressed as a marginal covariance matrix. For each marginal covariance of the locations of the scanner, we want to compute the greatest variability of the location. So how do we do that? We compute eigenvalues of the marginal covariance matrix. We select the largest eigenvalue, which corresponds to a variance. Then we take a square root of it so that we get standard deviation out of this and multiply it by 2 so that we get this 95% confidence level. And then this quantity is compared to accuracy bands, for example, as defined by RICS, or Americans have also their own standards. And depending on in which accuracy band this quantity will fall into, we colorize the point cloud accordingly. So for example, if the accuracy band is very high, so very strict accuracy level, then the point cloud will be green. Whereas if this quantity falls into a very poor accuracy band, then the point cloud will be red. And obviously by scene referencing, I mean the SLAM process, which I already explained in the previous slide. And all those colorized point clouds are accumulated, and this is how we get this whole point cloud of a building colored. All right, so to implement my method, I built such a handheld scanner and wrote its software. And I went to one of the colleges at Cambridge, and in real time I was reconstructing its courtyard that you can see here in this video. And on the left you see a stream of images from the camera, and on the right you can see this real-time reconstruction with overlaid accuracy bands or accuracy predictions. And at the beginning, the point cloud is green, as the drift in the trajectory is very low, so the uncertainty in the system is low. And as we progress, the point cloud turns orange here, and eventually this point cloud turns red, indicating that there is a high chance that the spatial error here is high. Therefore, I can take a corrective action to decrease this error by coming back to the place where I started scanning, and by doing so I can close so-called a loop, which in turn will decrease the uncertainty in the system and hopefully will increase the correctness of the point cloud. However, as you can see, there is still a region that is colored red at the top left corner. So in order to validate my method, I measured what the actual spatial error in this corner is and in this corner is. As you can see, this corner is greener or less red than this one. And to validate my method, I used a Faro scanner, a static Faro scanner, to get this very precise or very accurate point cloud, and I overlaid this point cloud onto this point cloud, and I measured basically the distribution of distances from this top region and from this region. And as you can see, this region, which is predicted as having low spatial error, indeed has a lower spatial error. The mode is around 10 millimeters. Whereas this region, which has been predicted with a higher spatial error, its mode is about 50 millimeters. So in such a way, I kind of validated whether the predictions of my system are actually correct. Moving to conclusions, in this paper we present a real-time, fully explainable method exploiting human-machine interaction to increase the correctness of point clouds produced by LiDAR-based mobile scanners. And with a 95% confidence level, our method predicts areas of high spatial error in a progressively created point cloud. Then the user can take corrective actions during scanning in an informed way. The method presented here has the potential to increase the accuracy of point clouds produced by LiDAR-based SLAM systems operating on pose graphs. This in turn might unlock demanding use cases such as engineering surveying or high accuracy measured building surveys which so far have been unreachable by mobile scanners due to systematic spatial errors in point clouds caused by drift. And finally, our method might contribute to reducing the effort put into scanning by giving real-time predictions on the quality of produced point clouds, hence eliminating the need for potential rescanning. All right. On the final note, our research received funding from BP, GeoSLAM, Langer O'Rourke, Topcon, and Trimble. We would like to thank these companies for making our research possible. And we also would like to thank Cambridge Enterprise for providing funds to patent this work. And with that said, I would like to thank the audience for watching. And now I am happy to answer questions. I think we have a couple of questions. Student at the Department of
Cool work. I have a quick question. So you're computing the eigenvalues in the post-covariance matrix, right?
Yes.
Most commercial suppliers will probably not give you access to the pose information on a handheld SLAM device. So when you're taking this and trying to apply it to devices, are you trying to sell the technology to the people providing this, or is it about as an add-on thing that you could compute it based on? Because if you're not having the pose information, can you somehow determine that just using the point cloud?
No, so you cannot determine this using, as you said, those commercially available scanners. And the only way to determine it is through, you need to have access to this underlying optimization on the pose graph. And this optimization is so-called maximum a posteriori estimation. And then you recover marginal covariances through certain real-time methods. And in my case, I had to implement SLAM from scratch, and this is how I got access to those marginal covariances. But I don't think that it's, I mean, if I cooperated with companies like GeoSLAM or those other manufacturers, then I guess we could agree on giving me this information, but yeah.
Very interesting work. I'm wondering, when you were looking to setting the plan for how to do the capture, you're looking into using landmarks. It seems that your method is very effective in providing a feedback to the user to do more loop closure, right? So every time that things are getting red, that means you go back and make sure that you readjust. I'm wondering if you look into detecting landmarks, markers that are typically available with either mobile scanning or laser scanning as a basis of reducing the spatial error from a planning perspective as opposed to execution. I understand this work is primarily on the execution scanning. So if you can comment on it, thank you.
Yeah, absolutely. So indeed, if we place some landmarks and you can detect those landmarks while scanning, and if we know the rigid body transformation between those landmarks, we can put this into the underlying optimization process, and indeed we can dramatically increase the accuracy. This is something I am also investigating, but this is actually, I already finished this, but I didn't present it here because those guys from Cambridge Enterprise told me that I should not reveal details. I think there is also a question there.
So thank you for your presentation. And actually your research is about to reduce the error. And I want to ask, like, is your research also include the part that way to improve the point data cloud? Point cloud data, because when I see your result, the root part is not coming where, and I want to ask, also, do you have some trial to improve the data?
So you mean like coverage of building?
Yeah.
I mean, this is not the point of my research, but you know, I think that if you in real time you see the point cloud, you see whether or not you covered a roof or not. And I think that by just real-time reconstruction, you can see whether you covered the area that you are interested in. This work is not about which area covered or not. This work is about really predicting accuracy of the point cloud.
Thank you.
Thank you.
Very much. Thanks a lot.